Matter, on the basis of the forces of attraction between the constituent particles, such as atoms, ions, or molecules, exist in three different physical states, namely gaseous state, liquid state, and solid state. You know that the constituent particles in gases and liquids are held together by relatively weak forces of attraction as compared to those in solids. As a consequence, they can translate randomly, rotate, and vibrate. Gases and liquids, thus, have the ability to flow and take the shape of their container. On the other hand, the constituent particles in solids are held together by strong forces of attraction. In other words, the constituent particles are closely packed. However, these particles can still vibrate about their fixed mean positions. Solids possess some characteristic properties attributed to their close packing. They have a definite shape and volume. They lack the ability to flow. They are incompressible. They are rigid. In general, the distinct properties of the three different states can be attributed to the arrangement of the constituent particles. In other words, any change in the arrangement of these constituent particles changes the physical state of a substance. In turn, the arrangement of the constituent particles in a particular substance depends upon the external conditions of temperature and pressure. For example, at 1 atmospheric pressure, water in liquid state gets converted into its solid form, ice, at 0 degrees Celsius or 273 Kelvin. Let us now understand how the molecules of water in liquid state attain the molecular arrangement of water in solid state. On cooling, the potential energy of the liquid molecules is released in the form of thermal energy. As a consequence, the space between the molecules decreases and the intermolecular forces of attraction increase. Also, the molecules lose their translator movement and rotatory movement, and they can only oscillate about their fixed mean positions. Thus, the molecules of the liquid attain the molecular arrangement of the solid. Let's take a quick look at how the structure and properties of a solid are correlated to one another. The nature of the constituent particles, the forces of attraction between them, and their arrangement together determine the structure of a particular substance. The properties of any solid substance ultimately depends on its structure. Hence, any change in the structure of a substance changes its properties. For example, the conductivity of silicon increases with the addition of impurities such as arsenic. So, a solid with the desired properties can be prepared by altering its structure. Some solid materials that were prepared for applications in various fields are superconductors, such as intercalated compounds of fullerenes, certain ceramics, synthetic biopolymers such as PHBV and PLA, and carbon nanotubes. Hence, the study of the structures of solids has immense significance in science and technology. Based on the arrangement of its constituents, solids are broadly classified into two categories. They are crystalline solids and amorphous solids. Crystalline solids have an orderly arrangement of their constituent particles, such as atoms, ions, or molecules, in 3 dimensions. They are arranged in an orderly manner to give a definite geometry to the crystal. Thus, a crystal is defined as a solid figure that has a definite geometrical shape, with flat faces and sharp edges. Quartz and sodium chloride are examples of crystalline solids. Now let's discuss amorphous solids. The term amorphous has been derived from a Greek word, omorph, which means shapeless. An amorphous solid consists of a number of constituent particles arranged in a random manner. Thus, amorphous solids do not have any definite geometry. There is short-range order, which means that there is an irregular arrangement of particles that repeats itself to a certain extent only. Glass, rubber, and plastics are examples of amorphous solids. In many respects, these solids resemble liquids. They flow very slowly at room temperature and are regarded as supercooled liquids in which the forces holding the molecules together are so great that the material is rigid, but there is no regularity in the structure. The flow of these solids is clearly observed in glass panes fixed to the windows or doors of old buildings. These are found to be slightly thicker at the bottom than at the top. The best example of crystalline solid is quartz, and of amorphous solid is quartz glass. Their arrangement is shown here. From these two images, you can clearly observe that both solids have similar arrangements. However, in quartz glass, there is short-range order. A crystalline solid has a sharp melting point. That is, when it reaches its melting point, it immediately changes into liquid form. These are considered true solids. Amorphous solids do not have sharp melting points. These soften over a range of temperature and can be molded and blown into various shapes. These solids behave as crystalline at a certain temperature. These are considered pseudosolids or supercooled liquids. Crystalline solids are anisotropic in nature. In other words, some physical properties like refractive index and electrical resistance change along with the change in the direction of the solid. This is due to the ordered molecular arrangement in the solid. Amorphous solids are isotropic in nature. In other words, they show the same physical properties in all directions. This is due to the random arrangement of the solid. If a crystalline solid is broken into pieces, the small constituents will have the same smooth and plane surfaces. Crystalline solids have definite heat or fusion values, while amorphous solids do not. Another important property of these solids is symmetry. Crystalline solids show plane of symmetry, axis of symmetry, and center of symmetry. On the other hand, amorphous solids do not show any symmetry. On the basis of the type of forces holding the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with molecular solids. The constituent particles in these type of solids are either atoms or molecules. The atoms or molecules are held together by weak forces of attraction. Further, on the basis of the nature of the intermolecular forces of attraction, molecular solids are divided further into non-polar molecular solids, polar molecular solids, and hydrogen-bonded molecular solids. Let's discuss each in turn. In non-polar molecular solids, the constituent particles are either atoms or molecules. The atoms or molecules in these solids are held together by weak dispersion or London forces. As a consequence, these molecules have low melting and boiling points. Hence, most of them are liquids or gases at room temperature and normal atmospheric pressure. For the same reason, they are soft. As the electrons remain localized to particular atoms or bonds, these are non-conductors of electricity. On the basis of the type of forces holding the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with molecular solids. The constituent particles in these type of solids are either atoms or molecules. The atoms or molecules are held together by weak forces of attraction. Further, on the basis of the nature of the intermolecular forces of attraction, molecular solids are divided further into non-polar molecular solids, polar molecular solids, and hydrogen-bonded molecular solids. Let's discuss each in turn. In non-polar molecular solids, the constituent particles are either atoms or molecules. The atoms or molecules in these solids are held together by weak dispersion or London forces. As a consequence, these molecules have low melting and boiling points. Hence, most of them are liquids or gases at room temperature and normal atmospheric pressure. For the same reason, they are soft. As the electrons remain localized to particular atoms or bonds, these are non-conductors of electricity. In polar molecular solids, the constituent particles, molecules, are formed by polar covalent bonds. Solid sulfur dioxide and solid hydrochloric acid are some polar molecular solids. The molecules in polar molecular solids are held together by relatively stronger dipole-dipole interactions. As a consequence, these solids have relatively high melting and boiling points. However, these are usually gases or liquids at room temperature and normal atmospheric pressure. Like non-polar molecular solids, these are also soft and non-conductors of electricity. In hydrogen-bonded molecular solids, like polar molecular solids, the constituent particles, molecules, are formed by polar covalent bonds. However, the bonded atoms in these molecules are essentially hydrogen and a highly electronegative atom, such as fluorine, oxygen, or nitrogen. Ice and solid hydrofluoric acid are two examples of hydrogen-bonded molecular solids. The molecules in these solids are held together by strong forces of attraction called hydrogen bonds. As a consequence, these solids have high melting points among the three types of molecular solids. Like the other two types of molecular solids, these solids are also non-conductors of electricity. At room temperature and normal atmospheric pressure, these are either soft solids or highly volatile liquids. The other type of crystalline solids is ionic solids. These solids have the ions as their constituent particles. The Coulombic or electrostatic forces of attraction hold the ions, cations, and anions together in the crystal. These cations and anions arrange regularly in three-dimensional space to form ionic solids such as sodium chloride, cesium chloride, and zinc sulfide. These solids have high melting and boiling points. This is attributed to the strong electrostatic forces of attraction. As a result, these solids are also hard but brittle. As the ions are in fixed positions, they are non-conductors of electricity in solid state. However, they are good conductors of electricity in fused or in their aqueous solutions. This stems from the fact that the ions acquire freedom of movement in their fused or aqueous solutions. You know that on the basis of the type of force that holds the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with metallic solids. In metallic solids, the metal atoms, such as copper, iron, silver, and magnesium, lose their valence electrons to the crystal as a whole. These solids are merely a collection of positive ions surrounded by and held together by a sea of electrons. Hence, the constituent particles in a metallic solid are positive ions in a sea of delocalized electrons. The electrostatic forces of attraction between the positive ions and the electron cloud constitute the metallic bonding, which holds the positive ions together. These electrons are not localized on any atom, but rather delocalized uniformly over the entire crystal. These free and mobile electrons make metallic solids good conductors of electricity and heat. The electrons flow through a network of positive ions when an electric field is applied. Similarly, when heat is supplied to one corner of a metallic solid, the free electrons spread the thermal energy evenly throughout the solid. The presence of free electrons also accounts for the luster and color in some cases. Metals are highly malleable and ductile. Metallic solids have fairly high melting and boiling points. The other type of crystalline solids is covalent or network solids. The constituent particles in these solids are atoms. These atoms are held together in large networks by covalent bonds. This interlocking network of covalent bonds extends throughout the crystal in all directions. Hence, covalent solids are also called network solids. They are also termed as giant molecules. Diamond, graphite, and quartz are some network solids. As the atoms are held by strong covalent bonds, these solids are very hard and possess very high melting points. These solids are non-conductors of electricity, except for graphite. In diamond, each carbon atom is bonded tetrahedrally to 4 other carbon atoms. Thus, a regular tetrahedral arrangement of carbon atoms bonded to one another in a 3-dimensional manner forms a network, resulting in a rigid giant molecule. Note that diamond is the hardest substance known and has a melting point of 3550 degrees Celsius. On the other hand, graphite is an exceptionally good conductor of electricity and is extremely soft. In graphite, each carbon atom is bonded to 3 other carbon atoms, resulting in hexagonal rings, which, when repeated throughout a plane, form sheets or layers. In its layered structure, the layers of hexagonal rings are arranged parallel to each other, as shown here. These layers are held together by weak van der Waals forces of attraction. The layers can slide over one another when impurities are present between them. On account of this, graphite is soft and can be used as a solid lubricant. As each carbon atom in graphite is bonded to only 3 other neighboring carbon atoms, the 4th valence electron is free to move about in different layers. Thus, the free mobile electrons account for the exceptional electrical conductivity in graphite. Crystalline solids have an orderly arrangement of their constituent particles in 3 dimensions. The positions of these particles in a crystal relative to one another are usually shown by points. An arrangement of an infinite set of these points is called a crystal lattice. Thus, a crystal lattice is a regular arrangement of the constituent atoms, ions, or molecules in 3-dimensional space. Sometimes, a crystal lattice, also called a space lattice or simply a lattice. There are only 14 possible three-dimensional lattices and are called Bravais lattices, after Auguste Bravais, a French mathematician who first described them. Now let's look at the characteristics of a crystal lattice. Each point in a lattice is called a lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. A crystal lattice can be subdivided into several cells, known as unit cells. Thus, a unit cell can be defined as the smallest portion of a crystal lattice, which, when repeated in different directions, generates the entire lattice. A unit cell represents the shape of the entire crystal. In fact, a crystal may consist of an infinite number of unit cells. A unit cell is characterized by distances A, B, and C along three edges, and angles alpha, beta, and gamma between pairs of edges. Alpha is the angle between edges B and C. Beta is the angle between edges C and A, while gamma is the angle between edges A and B, as shown here. Edges A, B, and C may or may not be perpendicular to each other. Unit cells can be broadly classified into two categories: primitive unit cells and centered unit cells. Unit cells in which all the constituent particles, such as atoms, ions, or molecules, are present only at the corners, are called primitive unit cells. Unit cells in which one or more constituent particles are present at positions other than its corners, in addition to those at the corners, it is called a centered unit cell. Based on the position of the centered constituent particle, centered unit cells are categorized into three types: body-centered unit cell, face-centered unit cell, and end-centered unit cell. A body-centered unit cell has constituent particles at all its corners, as well as one particle at its body center, as shown here. A face-centered unit cell has constituent particles at all its corners, as well as at the center of each face. An end-centered unit cell has one constituent particle at the center of any two opposite faces besides the ones present at its corners. You know that a three-dimensional crystal lattice is generated by the translation of lattice parameters A, B, and C. Based on lattice parameters, we have 7 popular crystal systems, namely cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. Let's discuss each in detail. In a cubic crystal system, all the three axes are of equal length and are at right angles to each other. The possible lattices are primitive, body-centered, and face-centered, as shown here. Sodium chloride, zinc blende, and copper are well-known examples of this type. In a tetragonal crystal system, the three axes are at right angles to each other, but only two are equal. The possible lattices are primitive and body-centered. Calcium sulfate and titanium dioxide are examples of this type of crystal structure. In an orthorhombic crystal system, the three axes are unequal, but all axes are at right angles to each other. The possible lattices are primitive, body-centered, face-centered, and end-centered. Rhombic sulfur, potassium nitrate, and barium sulfate are examples of this type. In a hexagonal crystal system, two edges are of equal length. Two angles are of 90 degrees and one angle is of 120 degrees. The only possible lattice is primitive. For example, graphite, zinc oxide. In a rhombohedral or trigonal crystal system, the three axes are of equal length and inclined at the same angle, but the angle is not equal to 90 degrees. The only possible lattice is primitive. Calcium carbonate and mercuric sulfide are examples. In a monoclinic crystal system, the three axes are of unequal length and only two angles are of 90 degrees. The possible lattices are primitive and end-centered. For example, monoclinic sulfur and decahydrated sodium sulfate. In a triclinic crystal system, the three axes are of unequal length and all angles are different, and none is equal to 90 degrees. The only possible lattice is primitive. Potassium dichromate, boric acid, and copper sulfate pentahydrate are some examples. You already know that every crystal lattice is made of an infinite number of unit cells, and every lattice site is occupied by a constituent particle that may be an atom, an ion, or a molecule. Now let's examine what portion of each particle belongs to a particular unit cell. Consider three types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distances between the atoms are greatly exaggerated. In reality, the atoms are packed much more closely together, as shown in the space-filling model here. The space-filling model shows that the atoms touch along the edges of the cell. By considering the portion of atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, it is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. However, there is one more atom at its body center. As a result, the atoms at the corners no longer touch along the edges of the cell in the space-filling model. The unit cell of a body-centered cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corner atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals, and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. It is clear that the atoms at the corners contribute 1/8 of their original volume each. In addition, there are 6 atoms at the 6 faces, which contribute half of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4. When substances form solids, they tend to pack together to form ordered arrays of atoms, ions, or molecules. Let's see how this order arises and what different kinds of arrangements are possible. Many a times, oranges or apples stacked nicely on a vendor's cart catch your attention. It is a practical application of close packing. A honeycomb is an excellent example of close packing found in nature. A close packing is thus defined as a way of arranging equidimensional objects in space, such that the available space is filled very efficiently. Solids are three-dimensional objects, and we will develop their structure in 3 steps. To understand how the constituent particles are packed, let us assume that these particles are hard spheres of identical size. First, let's look at close packing in 1 dimension. You can see that there is only one way of arranging the spheres in a 1-dimensional close-packed structure, that is, by arranging them in a row touching each other. In this arrangement, each sphere touches 2 neighboring spheres. In general, the number of nearest neighbors of a particle is defined as its coordination number. Therefore, the coordination number of a particle or sphere in 1-dimensional close packing is 2. Let's now look at close packing in 2 dimensions. When a number of rows are stacked up, a 2-dimensional crystal plane is generated. Obviously, there are 2 ways of stacking the rows. One way is for the rows to lie one above the other, with one sphere exactly above another. You can see that the spheres are aligned horizontally as well as vertically. If the arrangement of the spheres in the first row is said to be of A type, then the arrangement of the spheres in the successive rows is also of A type. The packing thus obtained is called AAA type packing. You can also see that each sphere is in contact with 4 other spheres, 2 on either side, 1 above and 1 below. Hence, the coordination number becomes 4. Also, if you join the centers of these 4 spheres, you will get a square. Therefore, this type of close packing is also referred to as square close packing. The other way is for the spheres of the second row to be seated on the first row in a staggered manner. That is, in the depressions of the first layer. The spheres of the third layer are placed in the depressions of the second layer, and so on. Evidently, the spheres in the third row are vertically aligned with the spheres in the first row. This pattern is followed throughout. If the arrangement of the spheres in the first layer is of A type, then the arrangement of the spheres in the second layer is of B type, and the arrangement of the spheres in the third layer is again of A type, and so on. The packing thus obtained is called AB-AB type packing. You can also see that each sphere is in contact with 6 other spheres, 2 on either side, 2 in the layer below, and 2 more in the layer above. Hence, the coordination number of a sphere becomes 6. Also, if you join the centers of these 6 spheres, you get a hexagonal pattern. Therefore, this type of close packing is also referred to as hexagonal close packing. If you compare the two arrangements, you can see that in hexagonal close packing, the constituent spheres occupy the space more efficiently. Therefore, constituent particles will arrange themselves in hexagonal close packing in a plane or 2 dimensions. Some spaces are left vacant after the close packing of the spheres. These vacant spaces are called voids or interstitial sites. In the figure, the empty spaces are seen as curved triangular spaces. These spaces left between the spheres can be divided into 2 kinds, B and C. The spaces marked B are the ones in which the apex of the triangular spaces is pointing downwards, while the spaces marked C are the ones in which the apex of the triangular spaces is pointing upwards. As real crystals are all 3-dimensional in nature, we will use this 2-dimensional hexagonal close packing to build 3-dimensional structures later on in this course. Solids differ from the other states of matter in that they have long-range order. To achieve long-range order, all the constituent particles need to be arranged in a symmetrical pattern in 3 dimensions. We will extend our knowledge of close packing in 2 dimensions to build symmetrical patterns in 3 dimensions. Let's first study 3-dimensional close packing from 2-dimensional square close packing. In order to build a 3-dimensional structure, it is easier to stack 2-dimensional square close-packed planes one above the other. As you can see, the spheres are aligned horizontally as well as vertically. If the arrangement of spheres in the first layer is considered to be of A type, then the arrangement of spheres in the subsequent layers is also of A type. This 3-dimensional arrangement is referred to as AAA type packing. If you look carefully, you will find that this arrangement has resulted in the formation of a simple cubic lattice. The unit cell of this lattice is a primitive cubic unit cell. Another way to build a 3-dimensional close packing is from a 2-dimensional hexagonal close packing. As you can see, the depressions of the first layer are the ideal seats for the next layer of spheres. By placing the constituent particles or the spheres in the depressions of the first layer, a second plane of closed packed spheres lying on the first plane is generated. It is important to note that when the spheres are placed on the voids of B type in the first layer, the C-type voids are left unoccupied as no sphere can be placed in them. As the spheres of the 2 layers are aligned differently, let the arrangement of spheres in the first layer be referred to as A-type and in the second layer as B-type. A closer look at the arrangement indicates the formation of two different kinds of voids, marked as O and T. If you look carefully, you will find that this arrangement has resulted in the formation of a simple cubic lattice. The unit cell of this lattice is a primitive cubic unit cell. Another way to build a three-dimensional close packing is from a two-dimensional hexagonal close packing. As you can see, the depressions of the first layer are the ideal seats for the next layer of spheres. By placing the constituent particles or the spheres in the depressions of the first layer, a second plane of closed packed spheres lying on the first plane is generated. It is important to note that when the spheres are placed on the voids of B-type in the first layer, the C-type voids are left unoccupied as no sphere can be placed in them. As the spheres of the two layers are aligned differently, let the arrangement of spheres in the first layer be referred to as A-type and in the second layer as B-type. A closer look at the arrangement indicates the formation of two different kinds of voids, marked as O and T. It is also called cubic close packing, CCP, or face-centered close packing, FCC. Metals like iron, copper, and silver crystallize in CCP structures. Further, as can be seen in hexagonal close packing and cubic close packing, a sphere has the coordination number 12. It is in contact with 6 spheres in its own layer, 3 more in the layer above, and 3 more in the layer below. Also, both the forms hexagonal close packing and cubic close packing are equally efficient in terms of filling up space. In both of them, 74% of the space in the crystal is filled up. Let us now look at the number of tetrahedral and octahedral voids present in these arrangements. In a close-packed structure, whether CCP or 8CP, if there are n spheres in the packing per unit cell, then the number of octahedral voids is the same as n, while the number of tetrahedral voids is equal to 2n. For example, in a CCP arrangement, if 4 atoms or ions are present per unit cell, then the number of octahedral voids is also 4, while the number of tetrahedral voids is 8.